So this video is a review of electron configuration and the concepts of orbitals. And so the Bohr model is a very simplified, which we looked at in the previous video. It's a very simplified version of how electrons exist in an atom. What we know now is that electrons actually do not just orbit around the nucleus. Instead, they are moving around in specific 3D regions where they are most likely to be found. Okay? And so these 3D regions are called orbitals. If you look for the s orbital, you've got 1s, 2s, and 3s. 1 represents the principal energy level. S represents the sublevel. So 1s is a sublevel, 2s is a sublevel, 3s is a sublevel. So for each of these sublevels, there is one orbital, meaning one 3D region where the electrons are most likely going to be found. For P, if you notice, there are three different orbitals, three different p orbitals in that p sublevel. So for example, if you had 2p, that is a sublevel, but there are three different orbitals, three different shapes, three different regions where the electrons will most likely be found. And so we're going to use this concept when we're talking about electron configurations in just one second. For D, for example, if you have a 3D sublevel, there are 5 different 3D shapes that electrons can be found in, that they're most likely going to be found in. Now, that does not guarantee that they're going to be within that region. That is where you find the greatest density of electrons, is within that shape. All right, so I'm going to go over the rules for writing electron configurations, and then I'm going to do an example with you guys. So first of all, electron configuration simply shows how electrons are distributed in the orbitals of the atom. So all of those orbitals that I just talked about. It explains how exactly they're distributed. Now, there are 3 different principles that we use when writing the electron configuration for an atom. The first is the Aufbau Principle. Now, the Aufbau Principle states that each electron occupies the lowest energy orbital that is available. Now, I'm not sure how you learned how to do this in Pee Wee chemistry, but I use a periodic table to demonstrate this. So I will show you how I do that just in 1 second once I go over the rest of these principles. The second is the Pauli exclusion principle. What that states is that there's a maximum of 2 electrons allowed in a single orbital, but they have different spins. They have opposite spins. And so we'll look at that when we draw out the orbital diagrams for specific elements. And then the last one states, is Hund's rule, states that single electrons with the same spin must occupy degenerate orbitals before additional electrons with opposite spins can occupy the same orbital. Degenerate simply means same energy. So you've got to fill orbitals with the same spin first, and then you can go back. And once again, when we go through this electron configuration and writing the orbital diagram in just 1 second, we will go over this to make sure this makes sense. So the orbital diagram simply represents how electrons are going to be distributed in orbitals. So let's actually look at an example of writing out the electron configuration and then writing out the orbital diagram. So I'm going to go through and I'm going to explain how to write the electron configuration for oxygen, and then I'm going to explain how you draw the orbital diagram as well. Now, I'm not sure how you learned electron configuration first year chemistry, but what I do is I use a periodic table. So as you can see right here, you've got 2 columns right here. This is your S sublevel, okay? This right here is your P. There are 6 of them. And then this is your D, okay? The only other thing for you to know is that since this is the 4th energy level, the only quirky thing is that D actually starts on 3, okay? But otherwise, everything stays the same. So you're going to start off, you're going to write first your energy level, then the sublevel, and then how many electrons you have in it. So for oxygen, I'm going to go all the way to right here. Okay, so this is going to be 1, because it's the first energy level. Then it's going to be S, and then you've got 1, 2 electrons, because you got to go all the way over. You're going from hydrogen all the way over to helium, so that's 1, 2. So it's 1s2. Okay, then I'm going to go to the second energy level, so it's going to be 2, and it's still S. And I've got 1, 2. So it's going to be 2s2. Then it's going to be 2. Now it's P, because I'm in the P sublevel. And I've got 1, 2, 3, 4. So it's 2p4. And that's all there is to it. So that is my electron configuration. Now, if, for example, I'd wanted to go to titanium, all I would do is I would say, all right, 1s2. Then I would do 2s2 right there. Then I would do 2p6 because I would include all of those. Then I would go down to 3s2. Then I would do 3p6. Then I would do 4s2. And then I would do 3d, and then it would be 1, 2. Okay? So this is following Aufbau's principle, because Aufbau's principle states that each electron is going to occupy the lowest energy orbital that is available. So if you follow the periodic table, you're automatically following Aufbau's principle. Now the next principle that we talked about was the Pauli exclusion principle. So if you look, remember, for S, there's only one shape, or one 3D shape, so there's one orbital for one S. So I'm going to draw just one box. That represents one orbital. Then for 2s, again, it's only one orbital, so I'm going to say 2s. For 2p, there are three different shapes, so there are going to be three different orbitals for this sublevel. So I do that. Now if I had, for example, 3d, there would be 5 orbitals. Now I'm going to fill it. So according to the Pauli exclusion principle, you can only fit 2 electrons in each orbital, and they must have opposite spin. Well, notice I only have 2 here, so that works perfectly. So I'm going to have one with an upward spin, one with a downward spin. For 2s, I'm going to have one with an upward spin, one with a downward spin, because it's 2s2. Now for 2p4, this is where Hund's rule comes in. Hund's rule says you have to fill orbitals with the same energy, then you can go with the electrons of the same spin, then you can go back and fill them with opposite spin. So I'm going to fill, because I need 4 electrons, 1, 2, 3, then I can go back and add a 4th. So while this seems silly, why don't I just fill 2 and 2 and leave this one empty? This is going to have a large role in how atoms actually interact with one another, and we'll look at that in this year. But this is just a basic review of the basic concepts of writing electron configurations. Now, if instead of writing out this whole electron configuration, I want to write out the condensed electron configuration, or the shorthand, what that allows me to do is actually to focus on the electrons, on the valence electrons, and represent the core electrons with a noble gas in brackets. So that brings up the question, what are valence electrons, what are core electrons? Valence electrons are your electrons that are in your outermost energy level. Okay? Core electrons are the electrons that are closest to the core, closest to your nucleus. So valence electrons are the only ones that we're concerned about for reactions, specifically forming compounds, forming ionic compounds, forming covalent compounds, etc., etc. Everything we've been talking about, that sharing of electrons, that's using valence electrons. So I'm going to show you how to do this, and then I'm going to expand it just to explain what core and valence electrons are. So what it tells you to do is to find your element, which for this one is nickel. So I find nickel, it has an atomic number of 28, so it's right here. Okay? And it tells you to move up and all the way across to a noble gas. So the noble gas I'm going to be looking at is argon. So I'm going to put argon in brackets. Okay? And then I'm just going to write out the electron configuration. So it's going to be 4, I'm going to just keep going. Okay? So 4s after argon, 4s2, and then it's going to be 3d8. Okay? So what this allows me to do, for argon, the electron configuration would have been 1s2, 2s2, 2p6, 3s2, 3p6. These are my core electrons. They have nothing to do with any of the reactions or formations of compounds that are going to happen. However, these right here, my 4s, the 2 electrons in 4s, and the 8 electrons in 3d, those will play a role when I am trying to determine what compound is going to be formed. And so that's what the shorthand electron configuration, or the condensed electron configuration, allows me to do. It allows me to focus on the valence electrons and ignore the core electrons. Really quickly, just as a review, because you learned this in first year chemistry, other than actually counting out valence electrons based on the electron configuration that's given to you, another thing that you can do is you can actually use the periodic table. So this group right here, the outermost electron would be 3s or 4s or 5s, so that's the outermost energy level. So this column right here, this group, has 1 valence electron. This group has 2. This group has 3, 4, 5, 6, 7, and 8 valence electrons. So this actually should ring some bells, because when we're talking about charges, this group has a +1, +2, +3, and then you get to -3, -2, -1, 0. So using valence electrons, that's actually how we determine the charge without actually talking about it. So if you notice, nickel, the reason why we didn't put number of valence electrons for these guys get kind of complicated, but at a very basic level, the outermost energy level that's given to you here is 4s, because 4 is your outermost energy level, which means the number of valence electrons for nickel is going to be 2. Now sometimes it's very obvious, but sometimes you've got your 3D here and you're like, wait, what about those 8 electrons right there? Well, that is why for nickel the charge can be variable, because you can lose more than these 2 electrons. You can even get into your d orbital. But if you have something basic without your d, then it's simply the outermost energy level, and the electrons there, those will be your number of valence electrons.